So good morning, students. Our today's topic is nucleophilic substitution reactions. In this nucleophilic substitution reactions, we are going to discuss two types of nucleophilic substitution reactions and their mechanisms. The SN1 reactions and SN2 reactions. SN1 and SN2 reactions. SN1 stands for substitution nucleophilic unimolecular. SN1 substitution nucleophilic unimolecular. SN2 stands for substitution nucleophilic bimolecular. Substitution nucleophilic bimolecular. So we are going to discuss these two nucleophilic substitution reactions, SN1 and SN2. Understood? Okay. So you can see there is this reaction. There is a nucleophile. There is a nucleophile. Nucleophile is a species with an unshared electron pair or lone pair of electrons. It has excess of electrons which it can donate. Okay. A nucleophile is a species with an unshared electron pair. It reacts with an alkyl halide or a substrate by replacing the halogen substituent. So this halide, the halogen is a leaving group in the substrate. So the halogen is the leaving group in the substrate. Okay, it is a kind of substitution. So this nucleophile substitutes the halogen, okay, in the alkyl halide substrate. So you can see this reaction. We have a nucleophile having lone pair of electrons or unshared electron pair, which it can donate. Okay, and this is the alkyl halide substrate. This is it may be chlorine, bromine, iodine, okay, halogen atom. Now, this nucleophile attacks the alkyl halide substrate. See, this gets substituted and the halide atom or the halogen atom, halide ion, it forms halide ion. This is the leaving group. It leaves the substrate. It leaves the substrates. So this type of reaction is known as substitution reaction. This has been brought about by the nucleophile. That is why it is known as nucleophilic substitution reaction. That is why it is known as nucleophilic substitution reaction. Okay. So this is our nucleophile having a lone pair of electron. Okay. It can donate a pair of electron. This is our substrate, an alkyl halide. Nucleophile attacks the alkyl halide. Okay. And it bonds with the alkyl group and it forces the halogen atom to leave the substrate. So the halide ion is formed. It gets removed from the substrate. Okay. So this is the leaving group. This one is known as the leaving group. Okay. In nucleophilic substitution reactions, the carbon hydrogen bond, carbon halogen bond, this X belongs to the halogen, or X represent a halogen. Okay. So this carbon halogen bond of the substrate, this carbon from the alkyl group and this halogen atom. So this carbon halogen bond of the substrate undergoes heterolysis, not homolysis. It undergoes heterolysis, and the lone pair electrons of the nucleophile is used to form a new bond. And the lone pair of electrons of the nucleophile is used to form a new bond to the carbon atom, okay? So in nucleophilic substitution reactions, the carbon halogen bond of the substrate undergoes heterolysis, heterolysis, and the lone pair electrons of the nucleophile is used to form a new bond to the carbon atom. Understood? To the carbon atom. Okay. So a nucleophile is any negative ion or any neutral molecule. It may be negative or it may be neutral. Understood? A nucleophile, it may be negative or it may be neutral. Okay. A nucleophile is any negative ion or any neutral molecule that has at least one unshared electron pair. Unshared electron pair. General reactions for nucleophilic substitution of an alkyl halide by hydroxide ion. So this is our hydroxide ion, or we can say hydroxyl ion. It has a electron, I mean, it has unshared pair of electron. Okay. This behaves as a nucleophile, negative species. Okay. Now this is our alkyl halide. So this nucleophile will attack the alkyl halide. This halogen atom will get displaced. Okay. This halogen atom will get displaced and this will be substituted. This will be substituted here on the place of halogen. So this is our product, an alcohol. This is our product, an alcohol. And this is our leaving group, alkyl. This is our leaving group, halide ion. This is our leaving group, the halide ion. Understood? This is a typical nucleophilic substitution reaction. A very easy nucleophilic substitution reaction. Understood? Now, okay, to be a good leaving group, the substituent must be able to leave as a relatively stable, it must be stable after leaving, weakly basic molecule or ion. It must be weakly basic molecule or ion. It may be in the form of a molecule or it may be in the form of an ion. Okay. So to be a good leaving group, the substituent, what are the substituent? What is the substituent? With the halogen, or the substituent which is leaving the substrate. Okay. To be a good leaving group, the substituent must be able to leave as a relatively stable. It must be stable in the solution after leaving the substrate. Okay. Weakly basic molecule or ion. In alkyl halides, the leaving group is the halogen substituent. In alkyl, as far as alkyl halide substrates are concerned, in these alkyl halides, the leaving group is a halogen substituent. Okay. It leaves as a halide ion. It leaves as a halide ion. Because halide ions are relatively stable, and they are very, very weak bases, they are good leaving groups. They are good leaving groups. They are good leaving groups. Understood? Now, nucleophilic substitution reaction, we are going to discuss about substitution nucleophilic bimolecular reactions. Substitution nucleophilic bimolecular reactions. Okay. So the rate of the reaction depends on the concentration of methyl chloride and the concentration of hydroxide ion. If we talk about the substrate, if the substrate is methyl chloride, alkyl halide, the alkyl halide is methyl chloride, and the nucleophile is hydroxide ion. The nucleophile is hydroxide ion. So in this case, it is bimolecular because the rate of the reaction depends on the substrate as well as the nucleophile. The substrate as well as the nucleophile. Understood? The reaction is second order overall because the rate depends on the nucleophile as well, the concentration of nucleophile as well as the concentration of alkyl substrate. That is why it is a second order reaction, bimolecular. The reaction is first order with respect to methyl chloride and first order with respect to the hydroxide ion. The reaction is first order with respect to the methyl chloride, the substrate, alkyl halide substrate, and first order with respect to the hydroxide ion or the nucleophile. This is the reaction. This is the reaction. This is the rate of the rate equation. Rate is directly proportional to the substrate, concentration of substrate, product, concentration of the nucleophile, concentration of the substrate and concentration of the nucleophile. So rate will be equal to K. K is the rate constant, product concentration of the substrate, product concentration of the nucleophile. So that is why it is known as bimolecular, because the rate of the reaction depends on the concentration of substrate and as well as on the concentration of the nucleophile, as well as on the concentration of the nucleophile. This is the reaction. See, this is methyl chloride. This is methyl chloride, and this is our nucleophile, hydroxyl ion or hydroxide ion. This is our hydroxide ion, nucleophile, having unshared pair of electrons. Having unshared pair of electron. Okay. So this nucleophile attacks the substrate from the backside. Attacks the substrate from the backside. You can see here the carbon has a partial positive charge and the chlorine has a partial negative charge. Chlorine is more electronegative than carbon. Chlorine is more electronegative than carbon. So chlorine will have a more negative charge. So it has partial negative charge and the carbon has a partial positive charge. Okay. So this nucleophile will attack the carbon. Okay. So the first step is formation of a transition state. Formation of a transition state. The first step is formation of a transition state. You see here, formation of a transition state. Formation of a transition state. The bond breaking and the bond making and the bond breaking. What is transition state? The bond is bond making. This is getting bonded to the carbon and this is getting broken. So bond making and bond breaking is taking place at the same time. This is the transition state. This is the transition state. So after this transition state, the product is formed, an alcohol. The product is formed, an alcohol. Methanol. This is methanol. Okay. And this is our halide ion, the leaving group. Halide ion, the leaving group. This is the halide ion, the leaving group. This, and it is stable. Okay. It will not take part in further reaction. Okay. Now this is our product of substitution. This is our substitution product. Understood? This is the free energy diagram for SN2 reaction mechanism. First, the nucleophile attacks the substrate. This is Z is the leaving group here. This is the nucleophile. X is the nucleophile. This is our potential energy. This is the reaction coordinate. This is the reaction coordinate. This is Gibbs free energy. Gibbs free energy change. Okay. See, during reactants, they have, their own potential energy, okay? But when the nucleophile attacks the substrate, okay? So bond breaking and bond making, transition state, it undergoes a transition state. It forms a transition state. This transition state, it has more potential energy than the reactants. More potential energy than the reactants. But once the products are formed, this leaving group leaves the substrate and the nucleophile bonds the alkyl group. It forms the product, okay? The substitution product is formed and the leaving group leaves the substrate. The potential energy, it becomes stable. The product becomes stable and the potential energy decreases. And the potential energy decreases. And the potential energy decreases. Understood? Yeah, this the same here. See, this is the nucleophile. This is our substrate. Okay. This is the transition state where the nucleophile is bonding to the methyl, and this chlorine, the halogen atom, is getting removed. Bond breaking and bond making taking place simultaneously in the transition state. So the transition state has more potential energy. Once this the product is formed, it becomes stable. The potential energy decreases drastically. Okay, so this is our product. The stable product is formed. Okay, and the leaving group leaves the substrate. Understood? Now, what is the stereochemistry in SN2 reactions? Stereochemistry in SN2 reactions. Stereochemistry in SN2 reactions. This is our reaction. The nucleophile attacks the substrate. The nucleophile is attacking the substrate. Okay. Now, this is our transition state, and this is our product. So you can see here an inversion of configuration. Inversion of configuration. If the substrate is R, the product will be S. So there will be inversion of configuration. If the substrate is R, the product will be S. If the substrate is S, the product will be R. So there is complete inversion of configuration. There is complete inversion of configuration. Remember this. This question may be asked. Okay, explain about the stereochemistry of SN2 reactions. Okay, so in SN2 reactions, there is complete inversion of configuration. Complete inversion of configuration. Complete inversion of configuration. Understood? Second order, the same thing. This is nucleophile. This is another substrate. This is another substrate. This is methyl bromide. And this is the same nucleophile. It attacks the substrate from the backside. This is our transition state, bond making and bond breaking. This is our product, okay, methanol. And this is the leaving group, halide. This is our transition state. This is our transition state. So the rate of SN2 reaction depends upon 4 factors. The rate of an SN2 reaction depends upon 4 factors. Remember these 4 factors. The nature of the substrate, the alkyl halide. The nature of the substrate means alkyl halide. The power of the nucleophile. The power of the nucleophile. The ability of the leaving group to leave. The ability of the leaving group to leave. The nature of the solvent. The nature of the solvent in which the reaction is taking place. The nature of the solvent in which the reaction is taking place. So we have four factors: the nature of the substrate, that is the alkyl halide, power of the nucleophile, stability of the leaving group, and the nature of the solvent. Understood? These are the mostly used solvents. These are some mostly used or generally used solvents for SN2 reactions. Dimethyl sulfoxide. This is for our general awareness. It is not asked in examination. Okay. Dimethyl sulfamide, no, dimethyl sulfoxide, dimethyl formamide, acetonitrile, hexamethyl phosphamide. So these are the generally used solvents. They are polar aprotic solvents. These, what is the nature of these solvents? They are polar, but they are aprotic solvents. They are polar, but they are aprotic solvents. SN2 conditions, the substrate, methyl, the reactivity of methyl is more than the primary alkyl halide. The primary alkyl halide is more reactive than the secondary alkyl halide, and the secondary alkyl halide is more reactive than the tertiary alkyl halide. Methyl is more reactive than primary alkyl halide. The primary alkyl halide is more reactive than secondary alkyl halide, and the secondary alkyl halide is more reactive than the tertiary alkyl halide. Okay. Nucleophile, negative charge is more reactive than the neutral. Okay. The leaving group stabilizes a negative charge. The solvent needs to be polar and aprotic. It must be polar in nature and it must be aprotic. It must be aprotic, polar and aprotic. So what is the reactivity order in SN2 reactions? Reactivity order in SN2 reactions. Methyl, reactivity of methyl is more than the primary alkyl halide. It is more reactive than the secondary alkyl halide, and secondary alkyl halide is more reactive than the tertiary alkyl halide. Why tertiary alkyl halide is least reactive? We can see why it is least reactive. Because in SN2 reactions, the nucleophile attack takes place from the back of the substrate, backside of the substrate, because the attack takes place from the back of the substrate because of the bulkiness of the tertiary alkyl halide, bulkiness of the tertiary alkyl halide. So this is the reactivity, the attack is not feasible. The attack is very difficult. It is not feasible. So that is why methyl is more reactive than the methyl is more reactive than primary alkyl halide. Primary alkyl halide is more reactive than the secondary, and the secondary is more reactive than the tertiary. Okay, understood? Now we'll talk about, or we'll discuss about, substitution nucleophilic unimolecular reactions. Substitution nucleophilic unimolecular reactions. Understood? First order nucleophilic substitution reactions, such as substitution nucleophilic unimolecular reactions. We have a tertiary alkyl halide here. We have a tertiary alkyl halide, and we have this nucleophile, and it is rapid. Okay, it forms this product, and this is our leaving group. This is our leaving group. So tertiary alkyl in SN1 reactions, we can see tertiary alkyl halides are essentially inert to substitution by the SN2 mechanism, as we have discussed. It does not, substitution is very difficult in SN2 reaction in case of tertiary alkyl halides because of steric hindrance at the backside of a carbon. Steric hindrance, or because of the bulky nature of these methyl groups. Because of the bulky nature of these methyl groups, there is steric hindrance. Because of this steric hindrance, the nucleophile cannot attack from the backside. Okay. Despite this, tertiary alkyl halides do undergo nucleophilic substitution reactions quite rapidly, but by a different mechanism. Such as the substitution nucleophilic unimolecular mechanism. Substitution nucleophilic unimolecular mechanism. Okay. So substitution nucleophilic unimolecular reactions obey first order kinetics. First order kinetics, such as the rate of the reaction depends on the concentration of the substrate. The concentration of the substrate. The concentration of the nucleophile is not of prominent, you can say, importance. Okay. It does not require the concentration of nucleophile, has least importance. Okay. So the rate depends on the concentration of the substrate. Okay. The rate depends upon the concentration of only one reactant, the alkyl halide, not the nucleophile. Okay. What is the order of the reactivity? The order of reactivity of substrates for SN1 reactions is the reverse of SN2 reactions. You can see here, tertiary alkyl halides are more reactive than primary alkyl halides. Primary alkyl halides are more reactive than secondary alkyl halide. Tertiary alkyl halides are more reactive than secondary alkyl halides. Secondary alkyl halides are more reactive than the primary alkyl halides, and primary alkyl halides are more reactive than the methyl group. Okay, and these groups. Okay, so this is our increasing rate of SN1 reaction. The order of reactivity. Understood? Now, this is the mechanism of SN1 reaction. Mechanism of SN1 reaction. There are two steps in SN1 reaction. Substitution nucleophilic unimolecular reactions. It proceeds in two steps. In step 1, there is formation of a carbocation. There is a formation of a carbocation. There is a formation of the carbocation. So this is our tertiary alkyl halide. So first, this bond gets broken. Okay, this this halide ion, it gets removed. Released in the solution. Okay, this is the leaving group. It leaves the this substrate, and there is a formation of carbocation. Stable carbocation. Formation of a stable carbocation. Now, then the second step, the nucleophile attacks the carbocation and it forms the product. The formation of the product takes place, and this is our leaving group. Okay, so reaction steps. The slower one, the step 1 is the rate determining step. Step 1 is the formation of carbocation. Step 1 is the rate determining step. The slower rate limiting dissociation of the alkyl halide forming a carbocation intermediate. Formation of a carbocation intermediate. The second step is a rapid nucleophilic attack on the carbocation. A rapid nucleophilic attack on the carbocation. Rapid nucleophilic attack on the carbocation to form the product. Understood? Note that the nucleophile is not involved in the slower rate limiting or rate determining step. That is why it follows first order kinetics. That is why it follows first order kinetics. Understood? The rate of SN1 reactions. The rate of SN1 reactions depend upon 3 factors. The nature of the substrate, the alkyl halide. The nature of the substrate, the alkyl halide. The ability of the leaving group to leave, the ability of the leaving group to leave. The nature of the solvent, the nature of the solvent. The rate is independent of the power of the nucleophile. The rate is independent of the power of the nucleophile. Understood?